Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, and here with another episode of Ask Dave. We're going to do something actually a whole lot different from what I've done in the past. I am finally going to approach something that I have been vigorously resisting for the past 3 or 4 years, and that is this, the nanoVNA. Okay, we're finally going to take a look at it. Now, I could just put this under the overhead and we could just quickly set it up for SWR and go, there you go. Well, you know me, we're not going to do that. I'm going to give you a little background on it as quickly as I can, and then we will actually set up the nanoVNA for taking SWR, and I have my hex beam is going to be the target antenna that we're going to take a look at, okay? So we're going to go through a few charts, and then we're going to set up the nanoVNA. And I really think you ought to stick with me through the charts, because by the time you're done with the charts, you'll have a far better idea of what you're looking at, okay? So let's take a look at the charts. This is the first chart right here. And yes, I bought my nanoVNA from Walmart, I think back in 2019, somewhere around there. And it's been sitting around ever since because I could never figure it out. Now, there's a ham on the front range, Tom Fryricks, who really worked hard to help me understand this thing. And I looked at it, I thought I had it, and then something changed, the menu changed, and I couldn't figure it out anymore. So I figured it out now. Now, how did I figure it out? Well, I mentioned in a previous video why I didn't think nanoVNA was very good, and it was in one of those commentariats where we really got into the discussion of the nanoVNA, and on one of the live streams where I finally was convinced, all right, I've got one, I'll look into it. The one I've got, this one, the Walmart one, and look at the price. They're only about $50. You can pay $75 if you want to. This one comes with the 3 things used for calibration and USB-C to standard USB connector, and that can be used to charge this. It can also be used to pull data onto the computer. Now, you will need, in addition, one more thing. And that is this thing that's dangling out of it right here. The actual sockets on here are little microwave connectors, SMA connectors. So we need something to convert that to an SO239. Now, you can get little sockets where you can just connect it right here, but that puts an awful lot of strain on the circuit board if you put a great big hairy cable on it. So this thing gives you a little more flexibility, and for HF, it will not change the results. Okay, so I asked ChatGPT through Microsoft Edge, what is the nanoVNA? And it said originated a few years ago, look how precise that is, from EDY555, a Japanese ham who released an open source project that constructed features of a vector network analyzer on top of an STM microcontroller based on some earlier work done by a group of hams in Texas on a software-defined radio. Now, this is interesting because what it means is this is a ham radio originated device. Now, a standard vector network analyzer is about $14,000. Okay, we're not going to worry about a $14,000 item. These things, as you saw earlier, are about $50. The original nanoVNA worked about 50 kilohertz to 300 megahertz. The new ones go up to 1.5 gigahertz. A bit about the battery, who cares? Okay, now what this measures is something called S parameters, or scattering parameters. By the way, this is amateur extra level material at this point, and then we're rapidly going to go past that. The scattering parameters, the S parameters are S11 is the input port voltage reflection coefficient. And that's the only one we need to know. S11 is the input port voltage reflection coefficient. You put a voltage into it and a voltage comes back. It's reflected back, okay? Now, when you hear that, you start thinking, SWR, right? Well, not quite. This is the actual percentage of the voltage that comes back. Now, there are a couple little kicks that go with this. First of all, here it talks about used to describe the behavior of linear electrical networks when undergoing various signal excitations. I guess you can think of the Beach Boys here. They've got their excitations. So here, a linear network, meaning a connection of capacitors, resistors, and inductors, and stuff like that. A linear network is a network that exhibits constant parameters, specifically resistance, inductance, and capacitance. Okay, those parameters do not change with changes in the input voltage or current, okay? And then they have this very laughable sentence right here. Working through a linear network is simpler than one might think due to its consistency of characteristics. Right, okay. Let's take a look at what's a vector. Okay, a vector has two dimensions. For example, a magnitude and a direction, or a magnitude and a phase angle. That's the one that really is of importance to us in ham radio. Now, you have some reference direction. You have an angle away from the direction, and you have a magnitude. So this vector right here is represented by its magnitude and the phase angle. Two elements. Now, the magnitude of the vector is called the absolute value. You've heard the term absolute value from your high school math class, and you were told it just means take the negative off and make it positive. Well, no, it means a lot more than that. The magnitude, the absolute value of a vector is merely the magnitude. And it doesn't matter in which direction it's pointing. It's always positive or zero. And it has no idea of direction. Let's take a flying example. Suppose I'm in my aircraft and my compass will point me toward magnetic north. Now let's suppose I do not want to go to magnetic north. I'd rather go to Grand Junction. Okay? So Grand Junction is like, and I'm guessing here, 35 degrees off of magnetic north, and it's over there by about an hour. Okay? That gives me a vector, a direction, and a distance. Or normally what you measure in an aircraft is speed. Speed is the magnitude. How fast are you going? Going 100 miles an hour, okay? And the reference direction is how many degrees away from magnetic north, okay? Or a properly calculated magnetic north. Now, in aircraft, we calculate from the reference direction down this way. This is the reference direction. We calculate it down this way and around to over here. Okay, so this is probably something like 330 degrees. Now, in electronics, the reference direction is not north or anything. It's in the positive direction of the x-axis, meaning you take a reference of the voltage that is exciting the circuit. That's your reference. The phase angle is calculated this way. Okay? So this is a phase angle of about 30 degrees, no, 25 degrees, okay? Positive 25 degrees. And so the magnitude is the voltage, or it could be the current. For example, if you want to say, here's the voltage, we usually measure the reference is the applied voltage, okay? And we might say the current is up here. It lags the reference direction. No, the lags would be down here. It leads the reference direction by a certain number of degrees. Therefore, it is capacitive. And the phase angle right here, if you take the cosine of the phase angle, that's the power factor. If you've ever wondered what the power factor is, that's where it comes from. So the absolute value of a vector is merely the magnitude, always positive, and has no element of direction. Now, remember we said that S11 is the reflection coefficient. The reflection coefficient is the voltage of the reflected signal divided by the voltage of the incident signal, the one that's hitting the antenna. Okay, now, this voltage might have a phase difference from this voltage. So rho, and that's a Greek letter, capital Rho, is a vector, okay, because it has not only the ratio here, but it has a phase difference, So this is a vector, two elements. It's got a value and a phase delay. Now let's just skip over to here. If rho is -1, that means a complete negative reflection when the line is short-circuited. So you send 5 volts to it, it comes back -5 volts. A reflection coefficient of 0 means no reflection when the line is perfectly matched. Remember, 50 ohms, going into 50 ohms, none of it comes back. Okay? That's your best case. Rho is +1 when the line is open-circuited. The voltage, if you put 5 volts in, you give 5 volts back. Okay? Now, this is extremely important right here. What we're measuring, S11 with the VNA, is the reflection coefficient. Now, the voltage SWR, VSWR, or just plain SWR. VSWR, SWR, same thing. If you want to sound like an engineer, you say VSWR. If you want to sound like a ham, you say SWR. Okay? They are the same thing, identically. So VSWR is equal to 1 plus the absolute value, meaning the magnitude, of the reflection coefficient divided by 1 minus the absolute value of the reflection coefficient, which is just the magnitude. Now, the reflection coefficient here, if you look up here, the reflection coefficient is always 1 or down to 0. It's between 0 and 1. So if the reflected voltage equals the incident voltage, you've got a reflection coefficient of 1, meaning everything is being reflected. If the reflected value is 0, and you've got some forward voltage, this is 0. So the reflection coefficient goes between 0 and 1. You might think of it like percentage. Okay, by the way, percentages would do similar things here, but let's keep it at 0 to 1. Mathematicians kind of like that. So do engineers. So here's your VSWR. So we are measuring actually the reflection coefficient. So it is very easy electronically in a microprocessor to convert the reflection coefficient to the SWR, which is what we're going to do. Now, let's take a look at a website, and I want you to memorize this website. It is extremely important. nanoVNA.com. Now, you'd think it being an open source project, it'd be .org, but it is not. It is .com. So nanoVNA.com will get you to this page. This is the official page for the nanoVNA project. Okay, and it's got a little description on the front here. I'd sure like to get an nanoVNA packaged like that, but I don't. Okay, now this is the menu about how to use it, how to read it, how to calibrate it. By the way, calibration is not something I'm going to talk about in this video. We're going to use SWRs close enough. We'll talk about calibration in a different video. You don't have to calibrate your MFJ thing, you just use it. And that's what we're going to do here. We're just going to use it. So, upgrades. Now, there's two apps here. One is an app where you can connect it to a computer and do things. The other one is the saver, which will allow you to visualize the data on your computer screen. And then there's a web client. We don't worry about that. There's the menu structure, and it is horrible. I'm going to show you that in a minute. There's a user group, and there's a buy a nanoVNA, okay? Now, I'm going to talk first about this saver app. Here's the saver. All right, it's software, and this is kind of what the screen looks like. You can get any kind of picture you want using any of the traces you want. Okay, we'll talk about traces in a minute. Now, here's something extremely important, and this comes from the menu, buy a nanoVNA. Okay? Here are places around the world you can buy a nanoVNA, and it'll be one that's, I'll use the term authorized, which is a meaningless term when you're talking about open source. But this is the one they want. And I'm pointing down here to Amazon, AURSINC. Now, they make a whole bunch of these with different features. This is the simplest. This is the AURSINC. That's what you search for. And if it's got that word in it, okay, then that's the one you're looking for. This happens to be one that's got all kinds of extras, cables, things like that. Okay, here's your little calibration things. You've got some cables and so on. And it talks about the different pictures of it and stuff like that. Now, I want you to look at this screen for just a minute. You see these different color drawings? Those are called traces. The yellow one's the one we're going to worry about. We're going to turn all the other ones off. You can turn them back on when you want to. Nothing illegal about that. But we're just going to look at one of the traces. And we're going to use it for SWR. Now, are you ready for this? This is the menu structure. Okay, sit back and gasp for a minute. That is just amazing. This up here is your top level menu. And we're going to wiggle around through this thing till we get SWR. I'm going to show you the simplest, easiest way to get it. Now, there are some words you need to know. Display is the root menu. Trace is one of 4 possible line or chart drawings. So there are 4 colors. Traces can be toggled on and off. We're going to toggle the second, third, and fourth trace off and use just the first one. Format. Now, this goes with a trace. You can have a different format for each trace. But a format is not whether you underline it or put it in capitals or whatever. It has nothing to do with the font. It is how do you want the data displayed. In our case, we're going to tell it that we want to take S11, which is the reflection coefficient, and display it as SWR. Okay? Stimulus. This goes all the way back to the beginning because this is in the main menu. Stimulus has nothing to do with actions by the U.S. Treasury Department or any state Treasury Department or anything like that. You may have received a stimulus check in the past, but it has absolutely nothing to do with what we're talking about here. A stimulus goes with a trace. So you can have up to 4. Stimulus goes with the trace. It sets the limits on the data display. Now, how do you get that from stimulus? I don't know. But if we want to set it for the 14 meter band, not 14 meter, 14 megahertz band, we do it through the stimulus, okay? Okay, so there we go. We have talked about some background about it, so let's look at the actual object. This right here is the box it came in. And what we have inside, this is the way it came. I came in some packaging, of course. This is the vector network analyzer right here, okay? Now, it's all charged up because I made sure it was charged up. It has 2 inputs. We're going to ignore channel 1 and go for channel 0. Okay, this is typical when you're playing with programmers. They start the world at 0, not at 1. You'd think it'd be channel 1, channel 2, but no, it's channel 0, channel 1. Okay, this is a USB-C, which can be used for charging it or putting something on the screen. All right, now it says that this is a credit card-sized device. So here's my veteran ID card. Choose VA. And that is how big the device is. It is literally credit card size, with the exception of the fact that these things stick out and these things stick out. So what have we got here? I'm going to bring this thing down a little closer so we can look at it. We've got the 2 inputs. We're only going to use this one. Okay, it's channel 0, and S11 comes here. This is S21, which we're not going to use right now. nanoVNA, wow, okay. Up here is your solitary USB, and it's USB-C. Here's you can turn it on like this, okay. And here is something, and this is a really weird looking thing. You can push it in as an enter, or you can turn it to one side or the other, which is the equivalent of an up-down button or something like that, okay? So this is kind of how it comes. Now, I mentioned here that there's one thing you need, and this is it, okay? This is the thing. This has an SO239 on it. This has the SMA, and it's a male, and this is the female here, and it goes on like this, okay? We hooked it up to the antenna, and this antenna is my MFJ hex beam. Okay? Now, I got something to help me. I went down to Verizon and picked this up for, it was 16 bucks. It's a little wand that you can use to touch things on these. Now, let's zoom way down. And in fact, in order for this to work, we have to put this up here. And we will zoom right down on it, okay? So we see the whole thing. Now, this is the top level menu. Well, not quite. This is the top level menu. Display, power, stimulus, and then we're going to come back to that stimulus, calibrate, which we can do later. Recall, you can store your calibrations, and before you use it, you will want to recall your favorite calibration, and then configuration of the thing. We're going to go to display, okay? And it asks about traces. So we will go there, and you will see that there are 1, 2, 3, 4 traces. Oh, I'm sorry, we've got programmers here again. It's 0, 1, 2, 3. Okay, these can be toggled on and off by just touching them. And it's on if the display. See, if I were to turn them all on, you would see different displays in there, and you can see them wandering all over the place. Okay, I don't know what they're formatted as. So we're going to turn all those off except for the one. Oops, trace. Okay, we've got just one. Go back. Now we're going to go to Format. Format. And we're going to format this trace as SWR right here. We just touched that. And now we've got SWR. Now the problem is that SWR is from 50 kilohertz all the way up to, what does it say here, 900 megahertz. Now we don't want that. So we're going to bring that menu up again, and we're going to go back, and we're going to go back, and we get up right here to the top level menu. Now we're going to hit Stimulus. And we're going to do this from, let's say, 13 megahertz. Okay. And then we're going to do it again. Okay, that was the start, was 13 megahertz. Now we're going to put in the stop, and we'll do 30 megahertz. Okay, and we can look at the SWR. Now see, we got the bottom one in wrong. So let's go back to Stimulus. Oh, start. And we'll do 1. Back. It's a little hard on the top of this thing here. 13 megahertz. Still says start 50 megahertz. Stop 30 megahertz, 50 kilohertz. All right, we're going to do the start again. 13 megahertz. There we go. Okay, we've got it in. Now, you see that at the bottom here is starting at 13 megahertz. Here's 14 megahertz. We've got 17, 15, 12, and 10. Okay, and that gives you the SWR. Now, if you want to know the SWR, that's where this cool little wheel comes in here. This cool little wheel moves that there's a little hash mark there. Okay, that moves that down to there. And then you look up at the top. Now we're going to go to stop and make it 15 megahertz. Now, did that take? No. Okay, it's got 13 megahertz down here and 15 megahertz. All right, you can see the trace right there. Now let's put this little marker by turning this thing. We're going to move that little marker down to the very bottom. Okay, and then read it out up here at the top. We see that this is at 13.946, and it is 1.24. Okay, now let's take it up through the 14 megahertz. There's the 14. And we take it up all the way to 14,340. So we're just about the top of the band. And we look at the SWR at the top of the band, and it's 1 point. It's under 2 to 1. I can't read it, it's so small. Okay, but what you see here is that this antenna is under 2 to 1 across the entire, I think it's 1.96, okay. It's 2 to 1 where it is there at the very top of the band. It's under 2 to 1 across the band. Now, there's no way to adjust this antenna to make that element a little bit shorter, because then that would put us, put the bottom of it right in the band. But the point is, we've done that. Let's pick a different band here, okay? And we're going to change the start to 21 megahertz. Okay, and the stop to 22 megahertz. Let's see if we got that in. Okay, we've got 21 megahertz, 22 megahertz. Now look at that thing. This line here is 1.5. That one, is that 1.5 or 2? 2. Let's bring this across just to be sure of that, okay? We can see right here where it starts to go up. Let's just take right there. Okay, the SWR in that position is 1.56. Okay, and the frequency is 21.53, which is outside the band. Okay, so what we see from having done this is that my hex beam is under 1.56 all the way across the band, which is really nice. The thing works really well. Okay, so let's recap. Okay, what we have shown here is that the nanoVNA is inexpensive, that it will measure SWR, that you have to remember to do the trace, tell it how to format the trace, and then tell what kind of stimulus you want on the trace, and then you could just move it around anywhere. And then you can hook it up to the computer and look at things and reformat them and so on before you go out and maybe make a change to your antenna. Now, will this device do more? Oh, holy cow, it will do more, okay? For example, if you're trying to make a trap for an antenna, this little device here will stimulate the trap. You can have the stimulus come out of here, go through the trap, and then come back here, and it will show you the frequency response of the trap. Okay, there's a million things that you can do with this thing. It is also possible, let me see if I can get it to do it. Back, display, trace. Okay, trace 0, back, format. It'll do Smith chart delay. Here's delay. Delay is very important because this is a time domain reflectometer, okay? And you can send a signal out and the signal will come back in, or you can put the signal in one end, take it out the other, and it will tell you the delay. Well, what does the delay tell you? It tells you how long it takes for light to go through that cable. Well, we know the speed of light in the cable. It varies with the type of cable, from anywhere from about 0.66 for really old cables to about 0.9 for more modern cables. And we apply that factor, and then we know within inches how long that piece of coax is. So there you have it, the VNA, the nanoVNA, where you can find authorized information, where you can find ones that you can buy that are endorsed or at least pointed to by the official organization. You've learned the terms that you need to know to get into the menu system and set your thing up right. We also learned that it can hang up once, and it did on us, okay? So there you go. The nanoVNA. Have fun with that. If you've gotten this far in this channel, I would encourage you to subscribe. Over half of the viewers do not subscribe, and YouTube thinks, oh, people aren't really interested in this channel because they visit once and then they never come back. I would encourage you to share this. I would encourage you to subscribe. It doesn't cost you anything. It doesn't hurt anything to subscribe. It just gives me a brownie point with YouTube, okay? And if you want to be notified of my videos, you have to click the bell too, okay? And if you would like to support this channel financially, you are absolutely welcome to do so. I had to buy that nanoVNA with channel funds. That's where that came from. And I also mentioned where to get that adapter too. They're very inexpensive. Go to dcastler.com/support. Find a way that works for you. And until we next meet, after you've tried out your nanoVNA, 73.